All right, get ready to explore because today we're taking a deep dive into particle physics, specifically trying to understand the Higgs boson.
Yeah, it's quite the puzzle, even for, people like me who study it every day.
Oh, I can only imagine. It's this incredibly tiny particle, but it's important for something so fundamental, how things in the universe actually get their mass.
That's the key. To understand the Higgs, you got to think about the standard model of particle physics. Think of it like the giant Lego set of the universe, all the fundamental building blocks that make up everything around us and the forces that control them, all organized. We got quarks, these super tiny particles that make up protons and neutrons. We have leptons, which include things you've probably heard of like electrons. And then we have bosons, which carry forces.
Okay, I'm picturing this cosmic Lego set, but where does the Higgs boson fit in?
Well, for a long time, the standard model had a big problem. He couldn't explain how particles had mass. The Higgs mechanism, with the Higgs boson as the star, was the missing piece. It says that there's this energy field, the Higgs field, that exists everywhere in space, kind of like a cosmic swimming pool, if you will.
Okay, I like this analogy.
So all the particles, those Lego blocks we talked about, they interact with this cosmic pool. Some particles, like Olympic swimmers, they interact a lot and gain a bunch of mass, while others just kind of dip their toes in and stay light. That's the basic idea of the Higgs mechanism.
So the more a particle hangs out in the Higgs field, the heavier it gets. That's such a cool way to explain something so complex.
The universe is pretty good at being complex. Now, the Higgs boson itself is like a ripple in this cosmic pool, a quick burst of energy in the Higgs field. It's that quick signal we're trying to find to prove that the field exists.
And that brings us to that big discovery back in 2012, right? I remember it being everywhere. Even people who don't usually follow physics were talking about it.
Yeah, after like decades of wondering and searching, scientists at the Large Hadron Collider, the world's most powerful particle accelerator, finally confirmed that they found a particle that looked like the Higgs boson. It was a huge deal for sure.
But that discovery was just the beginning, wasn't it? It's like we discovered this new continent and now we want to explore every corner of it. We don't just want to know the Higgs exists, we want to understand everything about it.
Exactly. And that's what we're going to be talking about today, trying to understand how the Higgs boson interacts with, well, itself.
Wait, the Higgs can interact with itself. It's like it throws a party and invites itself. Okay, now I'm even more curious. Tell me more about this Higgs self-interaction. Why is it so important?
Well, because it could either prove everything we know about the universe or completely change it. This self-interaction, it's sometimes called trilinear coupling, is a really important prediction of the standard model. If the Higgs works the way we think it does, then proving this self-coupling would be like finding the missing puzzle piece that completes the whole picture.
Okay, that makes sense. So we're basically talking about confirming the foundation of particle physics. But something tells me that actually measuring this self-interaction isn't going to be easy.
You're definitely right about that. It's honestly one of the biggest challenges we have in particle physics.
Okay, let's talk about that challenge. What makes studying this Higgs self-interaction so difficult?
To see this self-interaction, we need to see not one, but two Higgs bosons being created at the exact same time in the LHC.
So we need two of these super rare particles to just appear at the same time. That sounds almost impossible.
It's definitely not easy. And then, as if that wasn't hard enough, we need to be able to tell that they are actually interacting with each other.
That does sound incredibly difficult.
It is, and that's why this research is so interesting and important. If we figure out Higgs self-interaction, we'll understand so much more about the universe and its fundamental forces.
Okay, I'm hooked. How do we even start looking for something like that? So we're looking for this like super rare event, two Higgs bosons created together, and we need to see them interacting. It's like, I don't know, winning the lottery and then getting struck by lightning. How can we even begin to look for that?
That's where things get really clever in particle physics. This research paper we're talking about today, it looks at some really cool ways that we might actually be able to measure this Higgs self-coupling. They're focusing on the specific kind of Higgs boson we've actually seen, the one with a mass of 125 GeV.
So they're basically running simulations of these high-energy particle collisions, trying to create the exact situation where two Higgs bosons might appear and, like, interact.
Yeah, pretty much. But it's not just randomly smashing particles together and hoping for the best. They've come up with two main strategies to try to find any evidence of these Higgs self-interactions.
Two strategies. I like options. What are they?
The first way is called inclusive Higgs pair production. It's basically using a really wide net to look for Higgs pairs created in any direction during a collision.
Makes sense to me. Just look everywhere. What's the problem with that?
Well, the problem is that the signal from these Higgs pairs is super faint. It's easily lost in all the other particle interactions happening at the same time in the LHC. It's like imagine trying to hear someone whisper at a rock concert.
Ah, that pesky background noise. How do we even begin to separate the Higgs signal from all of that?
That's where the second strategy comes in, and it's even cooler.
Mm.
Boosted Higgs pair production.
Boosted. Like we're giving those Higgs bosons an energy drink or something.
Kind of. Imagine these Higgs bosons being created with so much energy that they fly out of the collision super fast. That's what we mean by boosted.
Okay, I think I see where you're going with this. We're basically making them stand out more, right?
Yes. Having that extra energy helps separate the Higgs bosons from all the background noise, making them way easier to see in all the chaos of a particle collision.
Smart. So instead of a whisper, we're making them shout so we can hear them over the music. But it still seems like we're searching for a needle in a haystack, even with the boost.
For sure. It's still incredibly hard. One way we usually try to find the Higgs boson is by looking for what it decays into. One common way is for it to turn into a pair of bottom quarks.
Back to those quarks, the tiny things inside protons and neutrons.
Yep. You might think, okay, if we need two Higgs bosons, why don't we just look for four bottom quarks? Seems logical, right?
Yeah, totally. What's wrong with that?
Well, this paper shows that even with the boost, just looking for four bottom quarks isn't enough. There are too many other things happening in the LHC that also create bottom quarks, so there's way too much background noise.
So even with our super fast Higgs bosons, we still have a huge mess to deal with.
Yeah, it's like trying to hear those two specific whispers at that rock concert, but this time everyone's whispering.
Okay, so four bottom quarks aren't going to cut it. What else can these physicists try?
Well, remember those computer simulations I mentioned earlier? They're super important in this research.
Right, the ones that simulate particle collisions. But those aren't perfect either, are they?
You're right to ask that. Turns out even our best simulations aren't good enough on their own. A lot of times they use something called an effective theory. It's basically a simplified way of doing the really complicated calculations so our computers can actually handle it.
So like a shortcut for physics.
Yeah, something like that. But the paper says that these simplified calculations aren't quite right when it comes to boosted Higgs production. They need to do the full, super complicated version, and that needs a ton of computing power.
Wow, that's intense. But I bet all this work with the simulations taught them some valuable stuff. What did they learn?
One really interesting thing they found was that not all Higgs boson decays are equal for measuring this self-coupling.
So we need to look at other particles the Higgs boson can decay into, not just those bottom quarks.
That's the idea. It turns out that decays involving tau leptons, which are heavier and more elusive than electrons, might be a better bet.
Tau leptons. Okay. Why are those so interesting?
Well, it's definitely tricky to study tau particles since they decay so quickly. The researchers think that their unique properties might make them easier to pick out from the background noise, maybe even better than the bottom quarks.
Huh. Interesting. So are we ditching the bottom quarks completely and just focusing on these tau leptons instead?
Not exactly. The researchers have a different plan.
So what's the plan then? We're not just giving up on bottom quarks entirely and switching to tau leptons, are we?
No, it's more nuanced than that. They actually suggest looking for events where one Higgs decays into, like you said, those bottom quarks, and the other one decays into tau leptons.
Oh, okay. So we're looking for both. That still seems really hard, like we're searching for a very specific grain of sand on a beach full of, well, other grains of sand.
It is, but the researchers found that if you look for these specific decays, but also look for them happening with a hard jet, it helps a lot.
Hold on, what's a hard jet again? Why is that important?
Okay, so imagine like a jet engine, but instead of blasting out hot air, it's shooting out particles. That's kind of what a hard jet is in particle physics. It's a bunch of high-energy particles all moving together in the same direction. And when you see that, those specific decays and this hard jet, it creates a really unique pattern.
So it's like a fingerprint, but for these particles.
Is it harder for anything else to look the same way?
All right.
Exactly. Like, think about trying to pick out a voice in a really noisy room. It's easier if that person is singing a song that only they know.
Right. That makes sense. So it's not just about what particles we see, but how we see them. That tells us if it might be this Higgs self-interaction.
Yeah, you got it. And the researchers went even further. They actually came up with a whole list of specific things to look for, like a map.
Wow. So they really thought of everything.
They're trying to make it easier to find this interaction because,
Yeah.
like we said, it's really important.
Right. This is way more than just proving what we already think. This could lead us to something completely new and mind-blowing.
Absolutely. I mean, if we do find evidence that this Higgs self-coupling exists, just like the standard model predicts, huge win. It would mean our understanding of how particles get mass is right on track. But here's the really cool part. Even if we don't find this self-coupling, or if our measurements don't quite match what we expect, it doesn't mean everything we know is wrong.
Oh, so it's like a win-win situation.
Pretty much, because if the standard model isn't the whole picture, then that just means there's something even more exciting out there waiting to be discovered. New particles, new forces, a whole new understanding of the universe.
That's incredible. This whole conversation has been amazing. Before we finish up, any final thoughts you want to leave us with?
Sure. One thing to think about is that all this research is focused on the Higgs boson we've already found, the one with a mass of 125 GeV. But what if that's not the only one? What if there are other Higgs bosons out there with different masses that we just haven't found yet? It's like what you were saying earlier, we might just be scratching the surface of all there is to know.
It really makes you think, doesn't it? I want to thank you so much for talking with me today. This has been a fascinating look into the world of particle physics.
Glad to be here.
And for our listeners, if you want to learn even more, check out the research paper we talked about today, Higgs self-coupling measurements at the LHC. Trust me, it's worth a read. Until next time, keep those brains buzzing.